Hello students, welcome to another session of online class. Today we will be discussing some numerical problems related to application of Gauss's law. So revising what we have learnt in the last class, we have studied Gauss's law, which says that total flux enclosed by a closed surface is equal to a charge enclosed by it. So total flux is obtained by using closed surface integral d dot ds is equal to q enclosed. So this is the mathematical formula which is required to calculate the total charge enclosed by it. So where d is the flux density. Okay, so today we will solve some of the problems which are related to application of Gauss's law. So let d, vector d is 4xy ax cap plus 2x square plus z square ay cap plus 4xy z az cap coulomb per meter square, and evaluate surface integral to find the total charge enclosed in the rectangular parallelepiped 0 less than x less than 2, 0 less than y less than 3, 0 less than z less than 5. So we have 6 surfaces. One is x is equal to 0, one is x is equal to 2, x is equal to 0, x is equal y equal to 0, y equal to 3, z is equal to 0, and z is equal to 5. Now we will see each surfaces and surface ds in each surface and the dot product how it will be. So first x is equal to 0 surface. So x is equal to 0 surface means in the xy coordinate, so the surface which is x is equal to 0 means the yz plane itself. Okay, so the yz plane itself is x is equal to 0 plane. So the we have x is equal to 2 plane also. So this is enclosing this one, right? So like this it is enclosing. So at x is equal to 0, the unit vector is in this direction, that is minus ax cap, and at x is equal to 2, the unit vector is plus ax cap. Because we are enclosing it with this surface, we have all the fluxes, we assume that they are moving outside, right? So x is equal to 0, it is minus ax cap, here it is plus ax cap. X is equal to 2, it is plus ax cap. Now so what is ds here? Ds will be, since x is constant, only things are dy and dz is ax cap. Here it is dy dz minus dy by dy dz ax cap. So what is d dot ds? So we will calculate this one so that it is easy to measure for us. So at x is equal to 0, you have to multiply with the entire d. You have to find the dot product with the entire d. So with this one you have to find the dot product. So ds has minus ax is there, so we know that. So only the dot product where the equal component, like ax dot will be 1 and ax dot ay will be 0 and ax dot az will be 0. So these two components won't be there. So only left is 4xy ax dot ax, so that will be 1. So minus is there, 4xy dy dz, and we know that x is equal to 0 here, so if you substitute, that will be 0. Okay, now x is equal to 2. The similar way can we find at x is equal to 2 what is happening? So we want to d dot ds. Again it is dy dz ax cap, right? So only this component will be left, so it will be 4xy dy dz, because ax dot ax will become 1 and remaining 2 will cancel. Now x is equal to 2, so it will be 8y dy dz. Okay, similarly we have to calculate at the components of y. So what are y's limits? Y equal to 0 and y equal to 3. These are the two surfaces. So in this one, y equal to 0 is this surface and y equal to 3 is this surface. So we have to enclose this one, so the surfaces will be here. Y equal to 0, it will be dx dz minus dx dz ay cap, because it is the direction is other way, and the components are dx and dy. So in this direction it will be dy dx dz ay cap plus. Okay, so at y is equal to 0 and y equal to 3, I guess, right? Y is equal to 0 and y equal to 3. So we have to calculate the d dot ds equal to so here 4xy ax cap plus 2x square z square ay cap plus 4yz az cap. So if you do the dot product with the ax cap dot ay will be 0, so this term won't be there. This term will be there, but this term won't be there. So you have something called 2x square plus z square minus dx dy. We don't have a y term here to substitute y equal to 0. So similarly, d dot ds in this case will be 2x square, this is minus, so in this case it will be plus 2x square plus z square dx, not dy, it is dx dz, so this will be dx dz. Okay, now the next is the next two planes. Z is equal to 0 and z is equal to 5 plane. So here the component is dx dy minus is there az cap, because it is moving up downward. So this surface is upward and it will be plus dx dy az cap. Now if you find the dot product d at z is equal to 0, d dot ds will be how much? So d dot ds will be ax component, ay component will cancel, so 4yz az is there, so 4yz dx dy. Substituting z is equal to 0, it will become 0. At z is equal to 5, d dot ds is similar, but it is here it was minus, so here it will be plus 4yz dx dy. It will be 4 into y into 5 dx dy, so 20y dx dy. So what we have to find is, we have to find the closed integral. So what is Gauss's law? According to Gauss's law, closed integral d dot ds is equal to q enclosed, right? So we have to calculate closed integral d dot ds. So closed integral d dot ds will be closed integral d dot ds at x is equal to 0 plus integral d dot ds at x is equal to 0, d dot ds at x is equal to 2 plus integral d dot ds at y equal to 0 plus integral d dot ds at y equal to 3 plus integral d dot ds at z is equal to 0 plus integral d dot ds at z is equal to 5. So if you substitute the values, the first one x is equal to 0 term. So at x is equal to 0 we have d dot ds equal to 0. Okay, at x is equal to 2 it is 8y dy dz. So it is 0 plus 8y dy dz. So what are the limits for y and z? Y starts from 0 to 3 and z starts from 0 to 5. Okay, plus next term at y equal to 0. At y equal to 0 it is 2 minus 2x square plus z square dx dy. At y equal to 3 is plus 2x square plus z square plus dx dz. Okay, dx dz. So substituting that here, one is minus 2x square plus z square dx dz plus 2x square plus z square dx dz. Okay, so these two cancel because they are opposite in sign. And next is z is equal to 0, plus at z is equal to 0 it is 0. So at z is equal to 5 it is 20y dx dy. So 0 plus integral 20y dx dy. Now what are the limits for x and y? X is 0 to 2 and y is 0 to 3. Correct? X is 0 to 2 and y is 0 to 3. Okay. So our final integral is limited to only two integrals now. Closed integral d dot ds is changed to double integral 8y dy dz, 8y dy dz with the limits 0 to 3 and 0 to 5 plus 20y dx dy, 20y dx dy. So for x it is 0 to 2, for y it is 0 to 3. So integrating 0 to 5 you can integrate later. So 8y is 8y square by 2 with the limits 0 to 3 dz plus here it will be 0 to 3 20y is a constant. Integral dx is x with the limits 0 to 2 dy. So this will be 8y square y square, so 4y square, so 4y square 2 4 times 4y square. So when y equal to 3 it will be 9, so 4 9s are 36, so 36 y square, so 36 not y square, so substituting the value of 3 9 9 into 8 4 36 minus 0, so 36 which is a constant can be taken outside dz plus x limit to 2 and 0 it will be 2, so 40 which can be taken outside integral 0 to 3 20y, so 40 into 40 is taken, so y dy. Okay, so integrating 36, integral dz will be z with the limit 0 to 5 plus 40 into integral y square by 2 with limit 0 to 3. So this will be 180 plus this will be 220 times, so 20 into y square with the limit 3, so it will be 9 minus 0, so 9 minus, so 180 plus 180, 360 coulomb. So this is total charge enclosed is 360 coulomb. Okay, so this is how you have to calculate the values. I think in the question it is coulomb per meter square, so the final answer will be coulomb. Okay, we'll discuss another problem also where a point charge of 0.25 microcoulomb is located at r equal to 0 and uniform surface charge densities are located as follows: 2 millicoulomb per meter square at r equal to 1 centimeter and minus 0.6 meter square coulomb per meter square at r equal to 1.8 centimeter. Calculate d, that flux density at a r equal to 0.5 centimeter, r equal to 1.5 centimeter, r equal to 2.5 centimeter. And the last question, what uniform surface charge density should be established at r equal to 3 centimeter to cause d equal to 0 at r equal to 3.5 centimeter. So it is like at r equal to 0 you have a charge, and at r equal to 1 centimeter and r equal to 1.8 centimeter you have surface charges. So this is a sphere, r equal to 1 and r equal to 1 centimeter and r equal to 1.8 centimeter. Okay, and the third question is we have to keep another charge at r equal to 3. That we'll see later. Now first question is question A is we'll note down the values. This will be 0.25 microcoulomb, right? And here it is, the surface charge density is 2 millicoulomb per meter square, and here it is minus 0.6 millicoulomb per meter square. The question A is at r equal to 0.5 centimeter, what is the flux density? So according to Gauss's law, the flux density or the flux passing through will be equal to the charge enclosed. So d we have to find. So d dot ds is equal to for q enclosed. So at r equal to 0.5, so I am drawing a enclosed sphere at r equal to 0.5. So charge enclosed is 0.25. So we know that for a point charge or in spherical coordinate system we have derived earlier, d is equal to q enclosed divided by 4 pi r square ar cap, right? So here q enclosed is 0.25 nano microcoulomb, so 0.10 raised to minus 6, and the area is 4 pi r square, so 4 into pi into r square is at 0.5 we have kept this one at 0.5, so 0.5 centimeters, so it will be 0.5 square into 10 raised to minus 4, since centimeter square will be minus 4. So this 0.5 square will cancel with 0.25. So 10 raised to minus 6, 10 raised to minus 4 will cancel with the minus 6, making 10 raised to minus 2. So left is 1 by 4 pi. That will be, simplify, if you will get 0.0796 into 10 raised to minus 2. So that will be 796 into 10 raised to minus 6, or 796 micro. This is AR cap is there, so AR cap micro coulomb per meter square is the unit for density, flux density. So micro coulomb per meter square, AR cap. Okay. The second question is at r equal to 1.5 centimeter. So at r equal to 1.5 centimeter will come here. So the charge enclosed is now 0.25 nano microcoulomb plus the charge in the sphere of radius 1 centimeter. So for that sphere, rho s is given as 2 millicoulomb per meter square. So Q will be rho s into area of sphere with the radius r equal to 1 centimeter. So it will be 2 millicoulomb, 2 into 10 raised to minus 3 into radius of the sphere will be the area, surface area of the sphere will be 4 pi r square. So 4 pi into 1 square into 10 raised to minus 4, because centimeter square is 10 raised to minus 4. So that is Q of Q at r equal to 1 centimeter. So now total charge enclosed for this sphere is 0.25 plus this one. So according to this, D is equal to Q enclosed divided by 4 pi r square. So Q enclosed is 0.25 micro 10 raised to minus 6 plus 2 milli, so 2 into 10 raised to minus 3 into 4 pi into 1 square is 1 into 10 raised to minus 4 divided by 4 pi r square. So where we are evaluating at this point where r equal to 1.5, right? We are evaluating at r equal to 1.5 centimeter. So that will be into 1.5 square into 10 raised to minus 4. So for simplification, I can take 10 raised to minus 6 outside. So what is left is 0.25 plus here 10 raised to minus 4 and minus 2. If we take 10 raised to minus 1 will be there. So it becomes 0.2 into 4 pi divided by 4 pi 10 raised to minus 4 pi into 1.5 square. If you simplify, you will get the value 0.0777 into 10 raised to, because 10 raised to minus 4 cancels 10 raised to minus 2 times, or 777 micro coulomb per meter square. So there is a direction is there always, AR cap will be there since this is a vector, so that much AR cap. Okay. Now the third case is we have to find it r equal to 2.5 centimeter. So r equal to 2.5 centimeter encloses all the charges, right? So charges are 0.25 microcoulomb plus 2 millicoulomb per meter square into 4 pi r square plus minus, so like this. So Q1 is 0.25 micro, Q2 we have calculated it is 0.2, sorry, how much, 2 millicoulomb, 2 into 10 raised to minus 3 into 4 pi 1 square into 10 raised to minus 4, and Q3 is how much? So Q3 is the third charge which is in the sphere, 1.8, so it will be minus 0.6 into 10 raised to minus 3, 4 pi 1.8 square into 10 raised to minus 4 centimeter square. So D is Q enclosed divided by 4 pi r square AR cap. So Q enclosed will be 0.25 into 10 raised to minus 6 plus 2 into 10 raised to minus 3 into 4 pi into 10 raised to minus 4 plus minus 0.6 into 10 raised to minus 3 into 4 pi into 1.8 square into 10 raised to minus 4 divided by 4 pi. So the r which we have to consider is at which point? 2.5 centimeters. So that will be by 2.5 square into 10 raised to minus 4. So if I take 10 raised to minus 6 outside from all the terms, that will be 0.25 will be left there. Here minus 4 and minus 2 or minus 1 will be there, which means 0.2 into 4 pi plus here if we take 10 raised to minus 4 and minus 3 minus 1 will be there, so 0.06 into 4 pi into 1.8 square divided by 4 pi 10 raised to minus 4 into 4 pi into 2.5 square. So the numerator will be 0.320 into 10 raised to minus 6 divided by 4 pi into 2.5 square into 10 raised to minus 4 will be if you simplify and find the final answer, it will be 40.7 microcoulomb per meter square. AR cap is there everywhere. AR cap. Okay. And the last case is we have to find what uniform surface charge density should be established at r equal to 3 centimeter to cos d equal to 0 at r equal to 3.5 centimeter. So we have to cos a d equal to 0 at r equal to 3.5 centimeter. So in the diagram we have to set up a r equal to 3 centimeter sphere, and we are evaluating at r equal to 3.5 centimeter. Okay, so at r equal to 3.5 centimeter we will be evaluating. So what value we have to set to this one? So as we discussed, total is equal to, we assume the charge required is x coulomb. Okay, so q1 is we have so far seen q1 plus q2 plus q3 plus x should be 0, so that the flux density will be 0. So x is equal to minus of q1 plus q2 plus q3. So in the last problem we have seen that q1 plus q2 plus q3 becomes 0.3t0 into 10 raised to minus 6. So that will be minus 0.320 into 10 raised to minus 6 coulombs. Now what we want, this is the x at the sphere of radius. Total x is the total charge at sphere of radius 3. So what is surface charge density? Rho s will be x by area. So that will be minus 0.320 into 10 raised to minus 6 divided by 4 pi into 10 to the power uh, the radius is what? At x is equal to 3 we have to evaluate, right? We have to keep it at x is equal to r equal to 3 centimeter. So r equal to 3, if you substitute, it will be 3 square into 10 raised to minus 4. So if you simplify, that will be 0.0283 into 10 raised to minus 2, or it will be 28.3 microcoulomb per meter square. So this is surface charge density, so minus is there, don't forget this. So minus 28.3 microcoulomb per meter square should be kept so that the total charge becomes 0 and the flux density will be 0. So that's all for today's class. We'll see more in the next class. Thank you.